Welcome to lesson 4. So we've been talking one sample T methods. Now we're going to talk about that special case where we are looking at matched pairs. So first off, what do we even mean by matched pairs? So a matched pairs t-test is going to take two quantitative measurements from usually or often the same individual, or two individuals that are somehow dependent on one another. So you might look at one time, I forget what they were measuring exactly. They had two inks. They used one ink on my right arm and one ink on my left arm, and then they subtracted the difference. So because my arm is related to, the other arm, how the skin on one of my arms reacts probably is related to how the skin on the other arm reacts. They wanted to keep those observations together. So they looked at just the difference there. Before and after, so pre and post measurements, those are really common. Anytime you have repeated measurements on the same individuals. Twin studies, I don't think they're as prevalent as they used to be, but definitely that's another popular one. And it doesn't have to be like, oh, identical twins. Sometimes they're like, oh, well, these two puppies from the same litter, so they're genetically similar. Or they might match them like based on, oh, well, we want individuals of the same, height, weight, and whatever, and have a list of features they want them matched on. And then one gets one treatment and one gets the other, or something like that. So it's a special kind of randomized block design. It's a matched pairs design. And we're only ever going to look at pairs. We're not going to look at something more complicated where there's more than two. So matched pairs, when we have this, we end up focusing just on the differences. So we might have measurement 1 and measurement 2, but we're really only going to look at the differences. So maybe measurement 1 minus measurement 2. So we're looking for the mean difference. Be careful, this is not the same as the difference in means, which will be next week. So usually we will use 0. Almost always, not always, but most of the time, zeros are claimed difference, mean difference. So you can have a null that's saying, hey, that mean difference, we're going to first say it's equal to 0, but then we're going to look at not equal. So we just want to know if there is a difference. Greater than 0 or less than 0, it's really, really important to keep track of what direction you're subtracting in for this part. Otherwise, it's really easy to get the sign wrong here. So it's absolutely very important to keep track of, is it measurement 1 minus measurement 2, or is it measurement 2 minus measurement 1? Absolutely keep track. Our t-test statistics is going to look really, really similar. So it's going to be I think we're using, so x bar d, so the mean difference observed in our sample minus, so the claimed is almost always 0. So minus 0, that ends up being x bar d on top, divided by, so the standard deviation of the differences, divided by the square root of n. And then our confidence interval, it's pretty much the main thing that's going to be different. So an n is just the number of pairs that you have. So x bar d plus or minus t star times our standard deviation of the differences divided by root n. Almost always 0 is the claimed average difference. It's very uncommon when it's not, but it does happen. I have seen it. And so, yes, degrees of freedom is going to be the number of pairs minus 1. So a lot of this is easiest to see by example. So we'll have a couple here. So we have Blastobike, and oh my goodness, is Blastobike this is an example that's been around for a little bit. They claim that their bike increases speed. Like, so basically if you take the Blastobike versus another bike, you'll go faster on this bike. And hence reduce routine times for cyclists. So someone is interested in testing this claim. They went ahead and they took a sample of 5 competitive cyclists, and apparently a simple random sample somehow. They had a master list of all competitive cyclists somewhere. And they asked them to record their time on whatever their bike was, and they asked them to record their time on the Blasto bike, and they should have randomly assigned which one they rode first, which bike, because the order you ride the bikes in is important. That would be a randomized design there. So we can assume the population of cyclists times is normally distributed, thankfully, because 5 is a really, really small sample size, and the times are recorded below. So we have cyclist 1, so they have, it was 29.1 minutes, I'm hoping. I mean, I can't think of anything else that'd be really comfortable and call it a route. So on their standard bicycle, it took them 29.1 minutes. Oh yeah. Blasto bike, it took them 28.3 minutes. And you have 5 of them. So we can take these differences. And so we want to know, on average, does Blasto bike reduce the cycling time? So we want to know, is that mean difference in times? Like, we need to keep track of which order we subtract in, but we want to know if there is a difference there. And specifically, are they faster on that Blasto bike? Okay, so starting off with stating what the question that we're looking at says, that average difference in times, specifically standard minus Blasto bike, that's the way I'm subtracting. Typically, we like to subtract so we get positive numbers, if we can. Is that greater than 0? Because if this improves times, it makes times shorter, right? So standard minus Blasto bike should give you positive values if you're improving your time on the Blasto bike. That's the idea. So you could say, hey, is the average improvement in time, is that greater than 0? However you want to put it, it can be a little tricky wording mean differences sometimes. So my parameter, first off, it's not just a mean, it's a mean difference. So mu d, d for difference. It's the average difference in route times. And I really can't stress enough, it's super important to make sure that we know what order you're subtracting in. So it's very specifically standard minus Blasto bike. It's perfectly okay if you subtract in the other direction, if you say Blasto bike minus standard, but it needs to be written down. The only difference is that your t statistic will be negative instead of positive, but it should be identical every other way. Except for your hypotheses, the sign will flip. So the null hypothesis is that there is no difference in route times, or that the average difference is 0. So if nothing interesting is happening, the Blasto bike does nothing to the average time, you're just going to say, okay, well, mu d is equal to 0. But because I am subtracting the order standard minus Blasto bike, if this bike is improving the times on average, I expect positive values to greater than 0. So this is a big part of where it's really, really important to know which order you're subtracting in. If I had subtracted the other way, it would be a less than sign. And then my significance level, they stated there 0.05. So that's what I'm going to use. And in general, if we ever give you a scenario where there is no significance level stated, 0.05 is a good default to go back to. But if we give you one, use the one we give. Okay, so actually finding the t-test statistic and doing this test here. So I have my 5 cyclists, and I have my standard, I'm going to say S, my Blasto bike is B. So my difference here, it looks like I'm doing standard minus Blasto bike. So standard minus B for Blasto bike. And looking here, I'm getting positive values. This generally suggests that I'm probably, it looks like on average people are improving their route times. I don't know how far this route is. 29 minutes is a lot farther than I go on my bike. So here you can pop these in to like use list in the under the stat button on a TI-83 or 4. The mean is just, that's your X bar D, so X bar D, so your average difference here. So of those 5 differences, if I average them, that is 2.26 minutes. And then my standard deviation for the differences, that's not really, it's really, really fast if you use like one var stats in your calculator. It's not as quick to do, you know, like manually by like either by hand or with a scientific calculator. It's 1.32, technically also minutes. And then ND, technically that's a D. My number of pairs, that's just 5. So I have everything I need to plug in here. I'm only really subtracting 0, that's the coin difference, so don't really need to subtract that 0 there. So 2.26 divided by 1.32 divided by square root of 5. 5's not a very big sample size. Most of the time we're going to be pretty bummed if you only have a sample size of 5. End up getting 3.83. So then we're going to still need a little bit more information in order to find a p-value. We're going to need degrees of freedom. So it's my number of pairs minus 1. So that's just 5 minus 1 is 4. And then we have a p-value there. Let's actually work on getting it on the next slide there. So if my t-stat was 3.83, degrees of freedom equals 4. So 3.83. I would want this upper. I also technically want both sides there, but yeah. Okay, so if I have a t-test statistic of 3.83, degrees of freedom 4, and I want to find a p-value, I'm going to start off with this degrees of freedom 4. It's going to tell me what row to use. So I'm going to use this degree freedom 4 row. And then I'm going to try to figure out where the heck 3.83 is. So looking here, it's not between these two numbers. No. Getting closer. Looks like it's between here and here. So then I go up and say, oh, well, my one-sided p-value, it's between, so remember, it flip-flops which one's bigger and which one's smaller here. So it's between 0.005 and 0.010. And we can't give full credit if you flip them around because we just don't count in that order. It doesn't make sense. So my one-sided p-value is between 0.005 and 0.010. Then you have to think, okay, is it one-sided? Is my test one-sided? So my alternative was mu d's greater than 0. So right there, it is one-sided, so now I'm done. This is my p-value. It's between 0.005 and 0.010. So if it was a two-sided test, I would just multiply by 2, and I'd get my my two-sided p-values between 0.010 and 0.020. So here are instructions for the TI-83 or 4. There's just really one extra step. You have to create a column of the differences, and it's pretty much a breeze making it. And then you just do that t-test function on the differences. It's the same as a one sample t-test on the differences, where that null value is almost always 0. Okay, now for calculating the 95% confidence interval for the mean difference in route times. So we're still dealing with that bike example. I recommend pressing the pause button, giving this a try before I work through. So before I get started, I like to write out what I know. So the mean difference time that we observed is at 2.26 minutes. The standard deviation of the differences was that 1.32 minutes. My number of pairs there, that's just five cyclists. My t-star, which you will need a t-table for, or calculator if you know how to use it, to get a t-star. And that's going to be what, 2.776. So this specifically is the t-star critical value when you have degrees of freedom of 4 and you're trying to get a 95% confidence interval. So that tells you what column and what row to look at. So if I want to set this up, x bar d plus or minus t star times sd over square root nd. I have everything I need to plug in. So 2.26 plus or minus 2.77 times 1.32 divided by the square root of 5. Absolutely, this stopped being mental math for me the second it was anything besides a square under that square root. I ended up getting B. And I'm going to throw minutes in there because the mean difference, it's in minutes. So with 95% confidence, the mean difference in times, or the mean improvement in times, like so, was 0.621 to 3.8999, however many nines, minutes shorter for the Blasto bike than when they rode the standard bike. So now putting that all together for our write-up. So 4-part write-up. The 2 parts for the hypothesis tell us, hey, are we rejecting or not? So if we have a p-value between 0.005 and 0.010, if you look on the TI-84, you can get something more specific. We're going to reject that null. That is a small p-value. It's smaller than our significance level of 0.05. We're going to reject. So there's convincing or very strong evidence that the Blasto bike reduced route times on average. Really, really important that the average is in there somewhere. So then, with that confidence interval we just found, with 95% confidence, the estimated average reduction in time is estimated to be between 37 seconds to 3 minutes 54 seconds, with a point estimate of 2 minutes and 15 seconds when using Blasto bike. It needs to be super clear, my order of direction, like, am I improving on the standard bike or am I improving on the Blasto bike? It needs to be really, really clear. So that's our Blasto bike example. I think the next one we have is a UFO example. So several years ago, who knows, probably even more, I don't know. I haven't had anybody nonchalantly ask me to take an IQ test. It just doesn't seem that normal to do anymore. I don't know. So they took a random sample of people that claimed to have had an intense experience with a UFO, so unidentified flying object, and measured their IQ. I am really slightly interested, like what is an intense experience? But, they didn't describe that. So researchers want to know if there's evidence that folks that report having an intense UFO experience have an IQ that's different than the general population. So in the U.S., so the accepted or known or whatever average IQ in the U.S. being 99.7, IQ points. IQ is one of those things you really don't have to write the units, but if you do, they're points. So when they took that sample, they took a sample of 45 people. The average IQ of those 45 people was 101.6 and a sample standard deviation of 8.9. We don't have a population standard deviation, so T-methods it is. So identify the parameter and population of interest. So we're interested in the mean IQ of all people that have claimed to have had an intense UFO experience. So this is just mu. Just mu. So mu is the symbol or notation, and this is in words or in context. And we will frequently ask for both. So the mean IQ of all people that have claimed to have an intense UFO experience. So state the null and alternative hypotheses. So it's going to be a mu equals in the first one, because we want to know about this population mean. And the value, it has to be a value that didn't come from the sample. So looking back real quick, when I write up my hypotheses, I should not use this. It doesn't mean throw this away, but this does not go my hypotheses. It has to come from here. It has to come from outside the sample. It's going to be this 99.7. Because we want to compare to this 99.7 of all the folks. And it's going to be 99.7 in both. So we want to know if it was different, right? We didn't say, oh, we think it's the average IQ of people with intense UFO experiences. We think it's higher. We think it's lower. No, it's just we want to know if it's different. So select a significance level. Let me see. It doesn't say. We are going to go with, oops, 0.05. So typically a significance level of 0.05 goes with a 95% confidence interval. We're going to go with this. If we don't specify the significance level, usually by default we're perfectly happy if you use 0.05. That's fine. So checking our conditions. So the sample was obtained using a random mechanism. So was it a random sample? I think they reported that, well, they took a sample. Well, it took a random sample here. So I'm not sure where they get this master list. They must have had a list of all people that reported having an intense UFO experience. There's some master list, and they took a random sample from them. But we're going to say yes. We want to know, hey, is the sample big enough that the central limit theorem is going to kick in? Well, we had 45. 45 is at least 30, so yes. So here, do we know the population standard deviation, sigma? No, but we have sample data. So we have access to, so we either have or can calculate this standard deviation from the sample S. So I'm going to use T-methods. Now, if I had said yes to number 3, I would have gone to Z-methods. But because I said no, but I have sample information, I can use T-methods. Oops. So here we have all of our information. Again, calculate a test statistic. So this is that claimed value, so that's that mu naught. A sample of 45. This is equal to our sample size n. X bar, that's just that 101.6. And a standard deviation from the sample, that's 8.9. So I have everything I need. I can plug it in. I have this here. So plugging in, do some math. I end up getting a t test statistic of 1.43. Then for degrees of freedom, so that's going to depend on your sample size there. N minus 1, so that's 45 minus 1, it's 44. So now it's time to look for that p-value. So I have a t statistic of 1.43 and degrees of freedom equal to 44. So looking here, this means, hey, I want the row with 44. I don't see a row with 44. So I have to pick between 40 and 50. Remember what I said earlier about rounding down? We have a sample of at least 40. It's not true we don't have a sample of at least 50. So I am going to pick the row with 40. And I'm going to look for where 1.43 is. So where 1.43, no, not yet. Looks like it's between these two. It's between 1.3 and 1.68. So my one-sided p-value is going to be between, so remember, flip-flops these orders. It's going to be between 0.05 and 0.10. So now getting to this question, do we want a one-sided or two-sided p-value? So remember that came down to that alternative that mu is not equal to 99.7. Because it's a not equal sign, it's saying, hey, I need a two-sided p-value. We have a one-sided p-value. So that means everything we have here, we have to multiply by 2. So times 2, times 2, times 2. So I'm going to get a two-sided p-value that is between 0.10 and 0.20. Which, as far as p-values go, anything bigger than 0.10 is big. So that's a pretty big p-value. So my p-value is between 0.10 and 0.20. Obviously, you're more than welcome to use the calculator. Just remember to pick two-sided, or if you pick one-sided, you have to take that p-value and multiply by 2. So writing my two-part conclusion. So now we have to say whether or not we're going to reject because we got a p-value of what we got at the significance level, and then we need to do that translation sentence. So, you know, those results make sense to literally anybody reading them. Because even to statisticians, it's really, really hard to tell what the heck you're talking about without context. Like saying, hey, average IQ scores, stuff like that. So, using a calculator, I got a p-value of 0.16. That's a pretty big p-value. So we're going to fail to reject the null hypothesis. We did not get strong enough evidence to throw it out. Because we were only using significance level of 0.05. So one sample t-test, two-sided. So if I'm using that spectrum of p-values, this is little to no evidence or very weak. So there's not enough evidence. There is, or weak evidence. I mean, there are a handful there that we're okay with. There's weak evidence to conclude that the average IQ of all people that have claimed to have an intense UFO experience is different than 99.7, which is the average IQ of the general population in the US. So there, we did not find good evidence that the average IQ score for folks that have had this experience is different than the general population. So that's it for our lesson here. That's it for week 2. I look forward to talking with y'all on the discussion boards.